inside, it's a wild ride. Come on! Ride on the magic school bus!
Yuck, this is salty. But where's all the salt? I don't see any salt in the water.
Yes, but what you're holding is a solution of salt and water. A solution is a homogeneous mixture, which means that you can't see the individual parts. It looks the same all around. The salt, along with other minerals, which are called solutes, are dissolved in the water, which is called the solvent. Whatever you have more of is the solvent. Because you have more water, you know it's the thing that does the dissolving. We call a solution where you can't see the solute, like this one, an unsaturated solution, which means more solute can still be dissolved. Now, if we add more salt, it becomes a saturated solution. You can see the undissolved solute at the bottom. As a solid solute dissolves in the water, the number of dissolved solute particles increases. Then they collide with each other and become solid again. That's why you can see the solid at the bottom.
Okay, but I'm so thirsty. Do you have anything to drink?
Yeah. Drink this.
This feels weird in my mouth. What's with all the bubbles?
Oh, that's because this Coke 2 is a solution. You see, the carbon dioxide bubbles and sugar and other ingredients are dissolved in water. So in the solution, what's the solute and what's the solvent?
The bubbles are a solute and the water is a solvent, right?
Yep. In solutions where water is a solvent, we call them aqueous solutions. When you're writing in an equation, you put AQ in parentheses next to it, like this.
Okay, but can you take away the bubbles? I want to drink soda without the bubbles.
Sure. To do that, we have to think about the factors that affect solubility, which is the amount of solute that can dissolve in a solution. If we want less bubbles, we'd want the solubility to decrease. The solubility of solids and liquids doesn't change with pressure, but for gases as solutes, solubility decreases when pressure decreases. So compared with a can that is closed, a can that is open will have less bubbles. Also, for solids and liquid solutes, solubility increases as temperature increases, but for gas solutes, like the carbon dioxide, solubility decreases as temperature increases. So, if we open the can and let it sit in the sun, like so, there should be less bubbles.
Cool. I'm not thirsty, but I'm hungry. Why aren't any fish biting? Do you know any good spots?
Have you tried deep shaded areas? Applying the factors that affect solubility, the most soluble areas would have low temperature and high pressure. Those areas would have the most oxygen, which lots of fish want. Try casting your line in that area.
Okay, here I go.
It looks shaded and cool.
Hey, I got a fish. That looks like a keeper. Looks like we'll be having fish for dinner. Come over to my place, I'll make fish stew. The first one, and fish fry with another one. Man, this water's taking forever to boil. My mom used to say adding salt makes it boil faster. Is this true?
Actually, it's the opposite. We can use what are called colligative properties to know why. Basically, a substance boils when its vapor pressure is equal to the atmospheric pressure. The particles of the substance vaporize, as represented by the up arrows, and exert a pressure. But these particles will also condense and become liquid again, represented by the down arrows. When particles vaporize and condense at the same rate, called equilibrium, the pressure exerted is called the vapor pressure. Now, if there is solute present in the substance, as seen here, the less particles can vaporize, thus the vapor pressure decreases, which is known as vapor pressure lowering. Of course, these particles are largely exaggerated, but to get our point across, we must draw them this size. So if the vapor pressure decreases, it will have to increase more to become equal to the atmospheric pressure, causing the boiling point to increase. In short, the water will boil slower if you add solute to it. Let's try to calculate how much the boiling point will actually rise using this equation, delta Tb equals Kbmi. Well, delta Tb is the change in boiling point, m is the molality of the solution, moles of solute over kilograms of solvent, I is the number of ions the solute breaks into, and Kb is the molar boiling point elevation constant, which depends on the solvent. So let's set this up. Say we added 5.84 grams of salt to the water, which is about 0.1 moles of salt. Kb is 0.512 degrees Celsius times kilograms of H2O over moles of particles. For m, we have 0.1 mole of NaCl over 0.5 kilograms of water, since 1 liter is 1 kilogram, and we have 500 milliliters. And I is 2, because NaCl breaks up into 2 ions, Na plus and Cl minus. So, we get a boiling point elevation of 0.205 degrees Celsius. That means adding 5.84 grams of salt will raise the boiling point by 0.205 degrees Celsius than if we boiled pure water. Since the boiling point of water is 100 degrees Celsius, the boiling point of this solution will be 100.205 degrees Celsius.
Well, that took a long time to explain, but water's already started to boil.
Yeah, there's one more colligative property called freezing point depression. It explains that freezing point decreases when adding solute because the solute interferes with crystallization. It helps explain antifreeze and rock salt for icy roads. But with the nice weather nowadays, we don't really have to worry about it.
Oh, that's why the ocean doesn't freeze in the winter.
Yeah. Do you still want to try calculating how the freezing point of this water would change if we added the same 5.84 grams of salt?
Sure, but doesn't the constant change since it's not boiling but freezing?
Right. It's the same equation as boiling point elevation, except you use Kf, which is 1.86 degrees Celsius times kilograms of H2O over moles of particles.
Okay, let me try. Kf is 1.86. We still have 0.1 moles of NaCl over 0.5 kilograms of H2O, and I is still 2.
That's right.
Okay, the decrease in freezing point is 0.744 degrees Celsius, right? Since the freezing point of pure water is 0 degrees Celsius, this solution will boil at negative 0.744 degrees Celsius.
Yep. Good job. Remember that the freezing point goes down and boiling point goes up when solute is added.
On a side note, you like fish stew, right?
Yeah, I guess. Are you sure you know how to make it?
Yeah, of course. I'm my granny's ultra top secret recipe. It calls for 6 grams of salt per 100 milliliters of water. How much should I put in it?
Well, you have 500 milliliters of water right here, so 5 times 6, 30 grams of salt. Usually, when we say how much solute a solution has, we use molarity or molality.
Malalo, what? What do those words even mean?
Molarity indicates moles of solution over liters of salt. Moles of solute over liters of solution, written with a capital M. We have 30 grams of salt. The molar mass of sodium chloride is 58.4 grams per mole, so we have 0.51 moles of salt. 0.51 moles over 0.5 liters is 1.0. So the molarity of the solution is 1.0 molar.
What about the other one? Didn't you talk about 2?
Yeah, the other one is molality, written with a lowercase m. We kind of saw this in our colligative property calculations. It's moles of solute over kilograms of solvent. Since we know the moles of NaCl, 0.51, we just have to find the kilograms of solvent. Water has a density of 1.0 grams per milliliter, so 500 milliliters is 500 grams. 0.51 divided by 0.5 is 1, so the molality of this solution is also 1.
So aren't they the same thing then?
No, these are not the same because the added solute didn't really affect the volume of the solution. Notice how the denominator for molarity is liters of solution, while the denominator for molality is kilograms of solvent. This could be very important, especially when you're mixing 2 liquids.
Oh, this stew is way too salty. I think Granny wrote the wrong thing.
No problem. We just have to dilute the solution a bit more. Let's try diluting it to 0.8 molar. We just need to add some more water. Try this equation. M1V1 equals M2V2, where M1 is the molarity of the initial solution, V1 is the volume of the initial solution, M2 is the molarity of the new solution, and V2 is the volume of the new solution. Since we know M1, V1, and M2, we need to solve for V2. M1 is 1.0 molar, V1 is 500 milliliters, M2 is 0.8 molar, so, after calculating, V2 is 625 milliliters. Since we have 500 milliliters, we just have to add 125 milliliters. Now see, Jason, if you see, it tastes better.
Yes, it tastes much better. I should tell my granny next time I see her.
You know, actually, You can make another saltwater solution, but with HCl and NaOH. You see, NaOH reacts with HCl to make NaCl and H2O, as seen in the equation behind us. But you need to calculate exactly how much to mix, otherwise the solution will be acidic or basic and be dangerous. We have right here a solution of 0.50 molar NaOH and 0.10 molar HCl. How much HCl should we add to react completely with the 100 milliliters of 0.50 molar NaOH? To set up the dimensional analysis like so, based on the chemical equation. Right, so we need 500 milliliters of HCl to react completely with the NaOH. Now we shall mix them. Now here's the salt solution. I wouldn't recommend doing this though, since we already have salt available to use. Better safe than sorry.
I think I'll remember that when I run out of salt. On a different note, I think the fish stew is ready.
Great. Is the fish fry ready yet?
Yeah, can you smell? It smells delicious. Let's eat. Weird, I don't know why the oil in this pan isn't coming out.
Oh, that's because oil is non-polar. It won't mix with polar water. Try using the soap. It has non-polar and polar properties to pretty much remove any substance.
Oh, is that why oil floats in water?
Yep. And that's why you can't make a solution with water and oil, or any non-polar and polar substance. Substances with similar intermolecular attractive forces tend to be soluble in one another. An ionic solid, like salt, is made up of ions which are attracted to polar water molecules by ion dipole forces. So salt is soluble in water. What do you think the intermolecular force between two polar molecules is called?
I don't know. Two polar?
Nope. They're actually called dipole-dipole forces. So a polar solute will dissolve in a polar solvent.
Oh, cool, man. Thanks for helping me fish and cook and wash my dishes.
No problem. I'm just glad I helped be a solution to all your problems.
Ha! Good one.